Okay, so before going to like I2C, basically, if I'm asking like I2C, it is like a serial protocol, communication protocol, or simple you can say low speed communication protocol. So communication means we want to do that. Just 1 minute. So communication means basically we need to do the data transfer from master to slave or slave to master. Okay. So now here comes a term protocol. So protocol means there are some predefined rules. Like if I'm asking you what is a RAM? Okay, so RAM means random access memory. So you can add your own required input and output. There is no certain rule defined. But if I'm asking you about I2C, I2Cs, there are certain rules. If you want to do the data transfer, then you have to follow those rules. And one company have that copyright of I2C. Like if you want to use I2C in your project, then you have to take permission from that company. Maybe your microchip or it may be NXP. Like here it is microchip and the NXP semiconductor also. Okay, so first this I2C it was invented by NXP semiconductor. Okay. So here protocol means there are certain. See, this is I'm saying simple understanding meaning. You can search your own definition from the net also. So there are certain predefined rules through which, or you have to follow, which you have to follow. Company have their copyright is. We have interface protocol also. You must have heard about FTP. This FTP, AHB, AXI. These are like interface protocol. ARM has its copyrights. Like if you want to use these things, you have to take permission from this ARM. Now coming to I2C. Okay, I'm not giving priority to here as your project is on this I2C. So it is a low speed. Yes.
Actually, our project is based on both interface and I2C protocol.
Okay, see, so whatever I'm going to explain you today, okay, this code, right? That code is basically on I2C. I know that you have I2C to FTP, so let's today concentrate on I2C.
Okay, you can directly start with the code, man.
No, see, directly code, see, before going to directly code, I need to explain you about I2C, how the data transfer happens. If once you are understanding how the data transfer happens, you can easily understand this code.
Yeah, okay. We are familiar with the I2C protocol.
Okay, no problem. So then can you explain me how, like, let I want to do the data transfer, write a data. Okay, I have one master.
Yeah.
I have one slave.
Starting.
Okay.
Okay. There will be there can be multiple masters and multiple slaves.
Yes.
Just assume there's a single master and multiple slaves.
Okay.
The master initiates the transaction.
Okay.
By starting a start bit, which is on when SCL is high, SDA should go from high to low. Okay. That's the start condition. Correct. And later the seven slave bits, slave address will be sent, 7 bits, and the 8th bit will be read write bit, and then the acknowledge will be sent by slave to the master.
Okay. So here now my question is, I have in the I2C master, I have 2 lines. One is SDA, one is SCL. So now in this SDA line, how it is a 1-bit line, and I have 8-bit data to transfer. Okay, again, I am doing address transfer first. So master will be sending the address to slave, then slave will send the response back to master. Now, how this thing happens with this 1-bit? Sorry, 1-bit data line.
Okay, there will be another line which is called SCL.
That is clock.
Serial clock line. Yeah. The SDA will be in synchronization with the SCL. That is, whenever at every passage of the SCL, the data transaction will happen.
Okay.
So if each bit will be sent at the positive edge of the SCL.
Okay.
So that's how the serially 8 bits will be sent. Set of
Okay.
8 bits.
Okay. So next what will happen? How here, what is the mechanism? How the slave is going to store this data here?
Slave will be having a shift register.
Okay.
It will receive the input data from the SDA and go on shifting the received data into the shift register.
Correct. Then see, whatever you said, only that memory's code is written. Okay. So let me just summarize the things. Okay. Then we will move to the code. Okay. So, so where I was, okay. So this I2C, it is a low speed communication protocol. We have other low speed communication protocol also. That is like your SPI. Some background noise is coming. Can all of you mute the system? SPI, I2C, and UART. So this I2C, what is the advantage of this I2C? It have only 2 lines. 2 lines means it will take less area, SDA and SCL. So it is the simple protocol, and we can have multiple master as well as multiple slave. Okay, so we can have multiple master and multiple slave. Please mute the system. Okay. So now I want to do the data transfer master to slave. It can be read or write or anything. Now you see in this diagram, I have single master and multiple slave. Okay, so in the first, what will happen? Master will send the start bit. Okay, so master is the one who starts the transaction. Slave is the one who responds the transaction. There is nothing like once is master means it will be always a master. No. If any of the component is starting the transaction, that will be identified as the master. So what will happen? I want to simply do some write. So first what will happen? Master will and start signal. Now, what is the start signal? I guess all of you know that is like your SCL is high. SL is high means it is working with respect to passage of clock. SL can be low also. Like you are working with negate of clock. It totally depends on how you are implementing the project. So SCL is high. SDA will go from high to low. If any of the slave is identifying this one, then slave will know that master is going to start the transaction. So in the Verilog code, how can I write it? At the rate passage, sorry, negate. At the rate negate of clock or negate of SDA. Why negate of SDA? Because SDA will go from high to low. So negate of SDA if SCL equal to 1. So this is my start bit. Means start signal master sending to the slave. Understood this part, everyone?
Yes, ma'am. Yes, ma'am.
Okay. So now what will happen? I have here 3 slaves. All the 3 slaves will get the acknowledgement. Okay, master is going to start the transaction. So next master will send the address. So this is the first. Master will send the start signal first. Then second, what will master do? Will send the address. Which address it will send? Slave address. I have 3 slaves. So in which slave I need to do the transaction? That slave address master will send. So here, master will send slave address plus 1 write and read bit signal. Whether you want to do read operation or whether you want to do the write operation. So how it is going to? It is going to send it 1 by 1. So here, what is the mechanism? At the rate passage of SCL, master will send SDA. From the slave side, slave will convert this serial data to parallel data. because in the slave, whatever the register we have, that will be 8-bit, 16-bit, or 32-bit, like that. So slave need to convert it from serial to parallel. That you said is shift register. So what is that shift register work? It will convert from serial data to parallel. Okay. So after getting the data, then slave will compare. Now see here, it depends on the implementation. Now you are getting a 8-bit value. Among that 8-bit value, how many bits are for register, how many bits are for write it, that is depends on your project. So here, whatever the value you get, slave will compare this address to its own address. All slave will have their own address. Okay. If the address matches, then that slave will send X signal. Okay. Other will send N. So what will happen? Physically, what happens? Already this slave address is some 8, this slave address is 9, this slave address is 10. Now master send one 8-bit value one by one, and remember it wait up to 8 clock cycle. Okay, so send the HDA for 8 clock cycle. Okay, so now how I am going to count the clock cycle? Here I need one counter. Okay, that counter will count for 8 clock cycle. 8 clock cycle means it is receiving the data. 9th clock cycle means it is the acknowledgement signal. This happens in the 9th clock cycle. So I need one counter that will be counting 0 to 9. Okay, so now what will happen? Slave will match with this address. Now let it is sending some 9. Then your first bit, remember LSB bit is the write read bit. Okay, let 0. This is 0 is the LSB. So 9-bit means it is matched with this slave. So now this SDA and SCL line will be connected to here, and here after the NAC signal, it will go to high impedance state. Okay, that means they are disconnected. Now this slave will only be connecting. Okay. So now here remember the 8-bit data received, LSB is the write read bit. It will say whether it is a write operation or read operation. Normally 0 means write operation, 1 means read operation. Okay, and other bit identified as slave address. So that means I can have maximum up to 2 to the power 7 number of slaves. Okay, so any doubt here how the address are getting transferred?
No, clear.
Okay. So now here you understood I need one start bit detection logic, one counter logic, one shift register logic. Then third, let's assume it is a write operation. Similarly, happen and see. Here I am explaining you up to like it is a 8-bit. Okay. Now let in the write you want to send 16-bit signal. Then same operation you have to repeat 2 times. Okay. Here in the address also let you want to send some 16-bit address. Then one high address, one low address. One, this is for sending the high address. Same logic will be repeated for sending the lower bit of address. So write operation, same method. I can simple copy paste. Why it is same operation? Because it is from master to slave. Write signal will be sent from master to slave. Okay, so master will send HDA. Slave will convert serial data to parallel. Slave now this is not required. Then after converting, slave will save this data. Okay, sorry. Before write operation, see, it is the slave address I have provided. Okay. Now after the slave address, I have some register address also. In the slave, inside the slave, some register address is also there. Now at which register I want to store. So I have to send the register address also. So that is register address. That means passage of SCL. Master will send SDA for 8 clock cycles. Slave will convert this serial data to parallel and it will store. And it will store that address. Now write operation, what will happen? Again, slave will get the 8 clock cycle data. It will convert from serial to parallel. Then slave will save this data in the register stored in previous step. Data with respect to the register previous step. Now here whatever the register I have got, it will store. Now here just assume instead of 8-bit you want to send 16-bit data. Then what will be the process? Same 8 clock cycle, 8 clock cycle. So first 8 clock cycle, slave will receive the data. Then it will send ACK or NAC. Then next 8 clock cycle, again it will receive data and send ACK or NAC. So same step. Why we are not taking a 16-bit or 12-bit register, instead of that we are taking 8-bit register? Because if I am taking 16-bit means again there will be more area. So instead of taking more area, what I am doing, I am just reusing that 8-bit register 2 times. So here it will take more time, like speed will be less, but area will be also less. Okay, so up to this, any doubt? Up to write operation, how the write operation happened?
No, clear.
See, once you understood like 50% of the code, you can easily understood. Okay. So now fix this stop. Okay. Now master has done the transaction. Now master want to stop. So here master will send stop signal. So what is the stop signal? When SCL is high, SDA will go from low to high. Opposite of start. Low to high. So that means at the rate passage of SDA, SCL equal to 1, then it is the stop. So when slave will receive the stop signal, it will stop all the transactions. Your transaction is completed. Now, if you want to do the read operation, then what will happen? Here master is sending the value in the write operation, but during the read operation at the first step, slave will convert parallel to serial format. This is also one shift register required. Okay, parallel to serial format. Then it will send the value to master. And after 8 clock cycle, master will send the ACK or NAC. 8 clock cycle. Master will send ACK or NAC. Okay. Now this thing's completed. Okay. So now my question is, I have this one part only. Now how slave is going to identify? Now see, just this is master, this is slave. So this is my SDA line. Just with respect to slave, this SDA can be input, can be output. It is bidirectional. Now, when it will be used as an input and when it will be used as an output? Because at a time, if let's slave is sending some data in this line, and at that time master is also sending data here, then data will be lost. So we have to control that. Okay, we have to control when this SDA will act like input and when this SDA will act like output. So for that, we can take one SDA enable signal. This is now let master is sending address. With respect to slave, I am explaining. Okay. Now during address or register address write operation. This SDA is the input to slave. So I can simply write if this SDA enable equal to 1, then SDA will act like input. And if this SDA enable equal to 0, then this SDA will act like output. It is like a MOX. In that MOX, I am deciding whether my signal will go from the slave or will come into the slave. So for that, I will be taking one SDA enable signal. Okay. So here you can simply write your main SDA signal is equal to, if this SDA enable, if it's equal to 1, SDA, or if it equals to 0, then SDA out. And in this condition, your SDA out means acknowledgement signal. Okay, either 0 or 1. And SDA means this data. Okay. So now, any doubt here? I'll be explaining code now. Any doubt in this code, like here?
Clear.
Okay. So now here we'll see what is happening. See here, this write protect pin, I have not gone through the document. I'm not sure why they are using this write protect. Okay. You guys can go through the document and may confirm. This A0, A1, A2, these are like your slave address or chip select, which chip you want to do the transfer. Then this HDA, SCL, normal I2C signal, then I have this reset signal. And these are some input signals. See, this SDA means it is like data out. And SDAO means it is like output enable. And all these signal during this explanation, you can easily understand why they are using all those signals. Okay. So here what they have done, this is the basically what your properties, whatever the I2C you are using. Okay. What is the SCL to SDA output delay, and what is the TWC means how much time it is taking to write into the memory. Some delay, because practically nothing is ideal. Everyone will take some time. So that delay they have defined here. SCL to SDA delay and how much time it is taking to write into the memory. Then all
that is delay for 1 bit to travel to
yes,
the SDA to SDA.
Yes.
Master to slave. Okay.
Yes.
And TWC is just for simulation they have given you used or what?
No. See, when you are writing to the memory, now let you send some 1-bit data. It will go to the slave. Then slave will write into the memory. So till then you have to wait. You cannot send the exact data after that. What will happen? That data will not be written properly to slave. Just come here. You received here, slave received one data, then it has some register. It is going to write that data into the register. Okay. So it will take some time. So that delay they have defined. It is the depending upon, see, whatever the logic you are using, at the end it will be some AND gate, OR gate, XOR gate. So practically all the gate have some delay. So whatever the technology you are using, depending on that technology, they have defined. Like if I'm going to use this circuit, this minimum, this delay is required. If I'm not giving this delay, then data will be lost. Okay. Then in the initial block, whatever the signals they have taken, they have initialized those signals to 0. If you are not initializing signal to 0, then what will happen? In the simulation, you may get some X value, unknown values. You will not be able, like it will be difficult to track why I am getting this X value. So initialization is important. Then this chip address, whatever the A2, A1, A0 you are providing, that is like your chip address. Okay. Now see, first master will send the start bit. So start bit negate of SDA. If SCL equal to 1, then start received is equal to 1. They have taken one start received signal. So whenever master is sending start bit, internally that signal value will go to 1. And all the other signals they have put 0. Any doubt here?
Clear.
It is simple. See, start bit detection, your start bit receipt is equal to 1. Because when start bit receipt is equal to 1, after that only slave will start taking the addresses or taking the SDA values from the master. Then here only they have defined stop bit. So for the stop bit, SCL equal to 1 and passage of SDA. SDA will go from low to high and SCL simple 1. Then here you can see they have made stop bit received is equal to 1. Okay. Now here you have remembered I have told you one counter value to count how many clock cycle. So they are just saying whenever the stop bit received, then I will make this counter value equal to 10. And in the start bit received, counter value will go to 0. Counter will start from the phrase. And when stop bit received, they are making this counter value equal to 10. I don't have to perform any other operation. So let the counter value be 10. Okay, done. Now this shift register, what is the work of this shift register? Converting serial to parallel. You can see serial to parallel and it is shifting from left to right to left. Means first it will be receiving the LSB bit. Okay, so let me add some points here. It is the shift register. It is converting serial. You are understanding this, or with some example I need to explain how this operation is happening?
No, we are getting
a simple serial to parallel. Okay. So now there is another counter. So what is the use of this counter? It will count for 8 clock cycle. 8 clock cycle means through the SDA data coming from master to slave. In the 9th clock cycle, it is either acknowledged on ACK or NAC bit going from slave to master. So this is the work of the counter. Okay, so after that I have this control byte register. Control byte register means basically it will have this operation. Slave address. Okay, this part. So now if you look, so it will first check start bit received, then bit counter value equal to 8. Okay, so if you look into here, so here already shift register have started receiving the values. Okay, now if you go to bit counter, where is that bit counter?
Is up.
Yes, up. So bit counter, when this bit count is less than 10, so it will start counting the values. So it has started counting. So when it will reach to 8 clock cycle, that means slave has received the shift register has get the 8-bit values. Okay. So now start bit received and bit counter value is equal to 8. Then write active is equal to 0. This write active basically it is the write read signal, I think. If you look here. Here this write active, why this signal is used. Okay, I will tell this later, but first let me explain what is happening. Okay, sorry, write active means 0 means already write operation has completed. That means into the shift register, write operation is completed. No more data shift register is taking. So when all these conditions are satisfied, so what they are doing, 7 down to 1. So this chip address values, they are storing here. And here they have taken one fixed value. See, this is total 7-bit value. My chip address is 3-bit. So rest 4-bit, they have taken this constant value. Okay. So now shift register. So this you understood, whatever the basically what is happening in this shift register, they are storing the chip address value. You understood this part?
I guess they are comparing. They're comparing the shift register value with
not storing. Correct. They're comparing. It is double equal. Sorry. So whatever the values they have received from here, they are comparing those values to the chip address. It will compare now. So which slave address value matches, that slave will only go on with the transaction. Okay. So now here they are comparing if this chip address value is matching means it will start the transaction. Okay. So now the 0 LSB bit, if it is equal to 0, then write operation. If it is equal to 1, then it is a read operation. Okay. So now whatever the values they got from this shift register, they are storing in this control byte. This is another variable. It will store the values there. So that means, and after that, the control receipt equal to 1. So control receipt is equal to 1 means slave will go to the next step, receiving the slave address. Okay, and they are making the start bit receipt is equal to 0. So understood this part? So here what they are doing, they are comparing with the slave address. So once the comparison is okay, then they are making whatever the LSB bit. If it is equal to 0, then write operation. If it is equal to 1, then read operation. This read write bit, this LSB again they are assigning. See, different if you go into the code, this read cycle, write cycle they are using for giving the delay. And this read write bit to identify whether it is a read operation or write operation. Okay. So now slave address part completed. So now coming to byte address register. Byte address, yes, tell me.
Hello, ma'am.
Yes.
Ma'am, why they are doing that as a negative edge of SCL?
Okay, so now here see, this part depends totally your implementation. Your I2c, it is an active low. Active low circuit. Okay, so now here what happens in the low, like when your SCL is low, then read write operation happens. When SCL is high, then either you start or stop. And see here I can say that this is the normal. Again, it depends on your implementation. Sometimes what happens, they use double edge. Okay, in with respect to lower clock or neg edge of clock, they will be doing some operation. With respect to pause edge of clock, they will be doing some operation. So what happens? The speed increases. Okay, so you have to check if all these like shift register write read operation happens with respect to neg edge of clock and I2c related happens with respect to pause edge of clock. Then in this code they are using dual edge of clock to increase the speed. Okay. Now see, if I'm explaining you, so here, one edge they will be using for all the internal operations. And when sending ACK or NAC signal, I have to check whether they're using same neg edge or pause edge. But for this ACK or NAC or SDA receipt, they are using this pause edge. That means they are totally using both the edge of clock. And in some cases, what happens for all the operation, they use neg edge of clock. Just for start and stop signal, they use this higher edge. Okay, these two situations are possible. Understood?
Okay. I thought they are doing that to reduce the clock cycle.
That's what I said. Dual edge of clock they are using means speed increases. Number of clock cycle will decrease, the speed increases. Okay. The two things. So what I said, okay, once it is getting disconnected, please connect again. So we have to check where they have used SCL, pause edge, and neg edge. After that, we can continue. Okay. So now here what happens, they are getting the slave address, sorry, register address. So in the register address, actually, if you look here, this is address high. This ADHI indicates address high. That means they are using higher byte of address, lower byte of address. Okay. So similarly, control bit received means they are sure that, okay, this step is completed. Once this step is completed, this control bit received is equal to 1. So they will be checking control bit received is equal to 1. Then bit counter value is equal to 8. Write read bit is equal to 0 means it is your write operation. So what will happen? Your start